All right, so let's take a look at a couple reactions and quickly assign oxidation numbers or oxidation states to these. So in the first example here, we have methane reacting with oxygen to produce carbon dioxide and water. So the first thing is that when you have an element in its natural state, so oxygen, for example, occurs as O2, the oxidation number for this is always going to be 0. So that's what the first line represent here is the oxidation number for each individual atom in that molecular compound. So in total, because each oxygen is 0, total oxidation number there is 0. Hydrogen, generally when it is in a compound, it has an oxidation number of +1. Okay, so we have +1 for each hydrogen, and we have 4 hydrogens, so that would give a total of +4, which means the carbon then has to be -4 oxidation number in order to cancel out. Because overall, when you add together oxidation numbers for a neutral compound, they should add together to give 0, right? So the +4 - 4 gives you 0. For CO2, oxygen, when it's in a compound, typically has an oxidation number of -2. And we have 2 oxygens in the formula, so -2 times 2 gives -4. The carbon here then has to be +4 to cancel that out. And then in the case of water, oxygen again is usually -2. Hydrogen is typically +1. We have 2 hydrogens, so 1 times 2 would give +2. The oxygen is -2. So add them together, you get 0. So what we can do then is we can look at the oxidation numbers for each of the species in our reaction and see how they change. So for instance, carbon here goes from -4 on the reactant side to +4. That's an increase in the oxidation number. Okay, and that means the carbon is undergoing oxidation. So the carbon is oxidized. If you look at the hydrogen, it looks like the hydrogen here starts off as +1. It ends up as +1. So nothing really happens to the hydrogen in terms of oxidation numbers. But if the carbon is being oxidized, something else has to be reduced. So if you look then at the oxygen, right, it starts off with an oxidation number of 0. It becomes an oxidation number of -2. So the oxygen there has a decrease in the oxidation number. So the oxygen then is undergoing reduction. It's reduced, which means that oxygen is a good oxidizing agent. And if you think about it, oxygen is probably the best oxidizing agent there is because that's what it does, right? When it adds itself to things, it oxidizes those things. So when you have your reactions, whether it's a simple combustion reaction like this or other reactions, you need to assign your oxidation numbers, see how they change from the reactant to the product side. If there's an increase in the oxidation number, that's oxidation. If there's a decrease in the oxidation number, that is reduction. So when we have redox reactions, we need to balance them. And when we balance our redox reactions, we are going to balance them by the technique known as the half reaction method. And this is going to include not just a regular balancing that you're used to, right? So we're used to balancing reactions based on mass. Okay, meaning that you have the same number and types of atoms on the left side and the right side. But now we're also going to balance reaction based on mass and charge, because your redox reactions are going to involve the movement of electrons and other types of charges, or other species that have charges as well. So let's take a look at a couple examples of how we do this, because we have a couple or generally two different situations in which we can encounter these redox reactions. So here we have a reaction to start off with. We have iron and the Cr2O7 2- ion becoming Fe3+ and Cr3+. So let's first of all assign the oxidation numbers. For iron, the oxidation number there is plus 2. For an ion, the oxidation number is simply the charge. In the case of the Cr2O7, so we know oxygen, when it's combined, it's usually -2 when it's in a compound. We have 7 oxygen, so 7 times -2 is -14. Okay, what that means then is that when we add whatever that -14 is to the 2 chromiums, what I should end up with is the overall charge, which is -2. So the two chromiums then would have an oxidation number of, what is this? 2 minus plus 14. So -2 plus 14 would give plus 12. So that means each chromium has to be plus 6. So the oxidation number here for the chromium is plus 6. On the product side, the iron is plus 3, and the chromium is also plus 3. So what happens to the oxidation numbers? Well, iron goes from plus 2 to plus 3. So iron, Fe, undergoes oxidation because its oxidation number increases. And that would then suggest that the chromium goes from plus 6 to plus 3. That's a decrease in the oxidation number. So the Cr undergoes reduction. So what we're going to do then is to separate this unbalanced reaction that we have to start off into a half reaction. So we're going to have a oxidation half reaction, and then we're going to have a reduction half reaction. And all we're doing for these half reactions is writing the species involved. Okay, so we have iron becoming iron 3 plus, iron 2 plus becoming iron 3 plus, iron 2 plus on the left, iron 3 plus on the right. And then whatever remains is there going to be the reduction half reaction, right? So we have here the Cr2O7, 2 minus becoming Cr3 plus, right? So we have our two half reactions that we are starting off with. That's the first step. The second thing that we need to do is we need to then balance each half reaction in terms of mass now with regard to atoms other than O's and H's. Okay, so if I look at the oxidation, I have 1 iron on the left, 1 iron on the right. In the reduction, I have 2 chromiums here on the left and 1 chromium on the right. So I'll need to stick a 2 in front of the Cr3 plus, right? So I balance the chromiums, or balance the atoms other than O's and H's. I don't have to mess with the oxidation one because I have 1 iron on each side. The next step would be to balance, after we balance the non-O's and non-H's atoms, we then balance the O's by adding H2O to the side where we need oxygens. So in the case of the Cr2O7, the reduction half reaction, you'll see that I have 7 O's here on the left side. I need to add 7 H2O's on the right to give me those 7 O's. Okay. So the oxygens now are balanced, but by balancing it using water, I've also now introduced some H's. How many H's have I introduced? 7 times 2, which is 14. I then need to balance out the H's by adding the H's to the left side. So that's 14 H pluses to the left. Okay. So we're over here now. We balance the O's by adding H2O, as many H2O as we need to balance the oxygens. Then we balance the H's by adding as many H pluses to the other side. Now, when I balance the H by adding H pluses, obviously now I also have additional charges that I've introduced. So now I need to balance my charges. So we've accounted for the atoms, right? So the mass balance. Now we need to think about how we balance the charges. So how do you balance the charges? We add electrons to the sides, whatever side that needs it. So in the oxidation half reaction, so this one here, all right, I have a 2 plus total charge on the left and a 3 plus total charge on the right. So electrons have negative charges. So if I want to make the total charge on the right side 2 plus, I would need to add 1 electron to the right side. Okay, so a 3 plus that 1 electron will give me a +2, which would balance out the -2 on the left. If I look at the reduction half reaction, okay, on the left side, if I look at the charges, and on the right side, so on the left side, I have 14 pluses, and I have 2 minuses. Okay, so I sum those together. What do I get? I get 12 pluses. On the right side, I have 2 times 3, which is 6 plus on the right. Okay, this 2 times 3 plus here. So what I need to do is I need to now add electrons to the side where there's an excess of positive charge. So that'll be this side. How do I make 12 plus become 6 plus? Well, I need to add 6 electrons, right? It'll take away 6 positive charges, and I'll end up with 6 remaining because I had a 12 to begin with. So I'm going to add 6 electrons to the left. We end up with this down here. And we've added 1 electron to the oxidation. We have that one. So once we've added those electrons, what you will see now is that we have an imbalance of electrons. So now we need to make sure that the electrons are the same in the oxidation half reaction and the reduction half reaction. So here I have just 1 electron. Here I have 6 electrons. So in order to make the electrons equal in the oxidation and reduction, I need to multiply this entire equation, this entire thing, by 6. And by doing that, I end up now with 6Fe 2 plus becomes 6Fe 3 plus 6 electrons. Right? So I multiply that first equation by whatever I need to, so the coefficient gets multiplied by a certain number, all the coefficients do, to make sure that I have the same number, same moles of electrons that I have in the other reaction. And the last thing that we need to do is we're just going to add together now the half reactions to cancel out those electrons. So I'm adding these two together. Obviously here, the electrons are going to cancel out. So what I end up with, when I add those together, I have 6 Fe 2 plus 14 H pluses plus the Cr2O7 2 minus to give 6 Fe 3 plus 2 Cr 3 plus 7 H2O. Okay, so that's your balanced equation, balanced reaction. And the reason why, by the way, that we can add the H2Os, for example, to balance the oxygens to begin with, is because a lot of these reactions are happening in aqueous solution. And aqueous means dissolved in water, so we can add H2O to them. We're adding H plus to balance because in most cases, these reactions are happening in acidic solution, so that's why we're adding H pluses. In some cases, we're going to encounter situations where the reactions happen in basic solution. So if that's the case, then we have a couple additional steps, and that is if it's happening in basic solution, then we add an additional step to this, which would be for every H plus that you see, we're going to add an OH minus to both sides of the equation. If it's occurring in basic, then we'd cancel out or we will make any additional cancellations by new water molecules. We'll take a look at an example here in a second. Okay, so when you balance your half reactions, when you balance your redox reactions, you want to use the half reaction method. We separate the overall initial unbalanced equation into an oxidation reduction, and then we start balancing your atoms first, other than O's and H's. Then you balance your O's by adding water to whichever side needs it. Then you balance your H's by adding H pluses to whichever sides that needs it. Then you balance the charge by adding electrons to whichever side that needs it. Then you make sure that you have the same number of electrons in the oxidation and the reduction by multiplying whichever one you need to by a number, the smallest whole number possible. And then we just sum them together. Okay, we can double check here that this equation is balanced. So let's check this one that we end up with. Let's see, we have 6 ions on the left, 6 ions on the right. 14 H's on the left, 7 times 2, 14 H's on the right. 2 chromiums on the left, 2 chromiums on the right. 7 O's here on the left side, 7 O's on the right. If we look at the charges, Okay, we have 6 times 2, that's 12 plus. We have a 14 plus, and we have a 2 minus. Okay, we add these together. We have 12 plus 14 is 26, plus minus 2, that would be 24, plus. If we add the charges on the right side, 6 plus 3 is 18, plus 2 times 3 is 6 plus. We have no other charges. 18 plus 6 is 24 plus. So charges are balanced, atoms are balanced. That's your balanced equation. All right, let's take a look at another one. This one is happening in basic solution. So we have cyanide plus the manganate to produce CnO minus and MnO2. So let's take a look at the oxidation numbers here. We have carbon, the nitride. Well, let's just break it up. And I'll leave the assigning of the oxidation numbers to you to do as you go through this example. All right, so the oxidation half reaction here would be the cyanide becoming CnO minus. The reduction would be the whatever remains, right? So this is the two things that are related, and then those are the other two that are related to each other. So oxidation, and we have then our reduction reaction as well. So first thing we need to do is to balance each half reaction with respect to atoms other than O's and H's. Well, let's see, we have a carbon here on the left, carbon on the right, nitrogen on the left, nitrogen on the right. So that looks fine. Reduction, one M on the left, one Mn on the left, one Mn on the right. So that looks fine. Next step we want to do is to balance the O's. So in the case of this first one, right, we have an extra O on the right side, so we'll need to add an H2O on the left to balance that extra O. Here we have 4 O's on the left side. We have 2 O's on the right, so we need to add 2 more H2O's to balance the O's on either side. And the next thing we need to do then is to balance our H's by adding H pluses to the side, or the side opposite to where we added the H2O. So you have two H's there. We need to add 2 H pluses to this side. We have 2 times 2, 4 H's on the right. We need to add 4 H pluses here on the left side. Okay, so we have up to this point, we're over here. Okay, the next thing we need to do is to balance out the charges by adding electrons. So on the left side here, right, we have a total of 1 minus charge. On the right side, we have 2 plus and 1 minus, so that gives 1 plus. So we would need, in order to, we can only make the charges more negative, right? So we wouldn't need to add any electrons to this side. We need to add electrons to that side. How do I make a 1 plus into 1 minus? I'm going to add 2 electrons to this side. And then if I take a look at the reduction half reactions, I have 4 plus here and 1 minus. So that gives 3 plus on the left total. On the right side here, it's 0. Okay, so how do I make the more positive side the same as the more negative side? I need to add 3 electrons, yes, to the left side. Okay, so we end up then with our equation, our half reactions at this point, balance in terms of charges and atoms. The next step we need to do is to multiply both of these, or either of them, to make sure that the number of electrons is the same on both sides. So we have 2 electrons in one, 3 in another. Well, obviously 2 doesn't go into 3 and a whole number of times. So the lowest common multiple of 2 and 3 would be 6. So I need to multiply this entire thing by 3, this entire equation, which means I need to multiply the second one by 2. So that I end up with 6 electrons. So what I get here is, remember, when you multiply by this number, all of the coefficients get multiplied by that number. So I end up with 3 H2O plus 3 Cn minus to give 3 CnO minus plus 6H plus plus 6 electrons. And then if I multiply the second one by 2, I end up with 6 electrons, plus 4 times 2 is 8 H pluses, plus 2 MnO4 to give 2 MnO2 plus 4 H2O. Okay, so at this point, okay, we're over here. And then we're going to add these two reactions together. So obviously the 6 electrons are going to cancel out. That's why we multiplied each of those by the number to begin with. So we sum these together, and we just write what we're left with. So we have the 3Cn minus plus the H. Well, let's see here. Not only do the 6 electrons cancel out, right? Because we have the same number on both sides, but there are other things that can cancel out as well. So these go away, okay? And if you look, now I have 6 protons here on the right, 8 protons on the left. So those 6 protons go away. We take 6 out from the 8, we end up with the 2 protons left here on the left side. Similarly, I have 3 H2Os on the left, I have 4 H2Os on the right. The 3 H2Os will cancel with 3 H2Os here, and I'm left with 1 H2O on the right side. And then I'm just write what remains. I still have the 2 MnO4s. On the right side, I have this 3 CNO minuses, the 2 MnO2s, and the H2O. So what we'll see at this point, right, is what we would get normally, but the extra steps involved now is the fact that this is happening in basic solution, which means now we're going to add an OH minus, a hydroxide, for every H plus that we see. And we're going to add it to both sides of the equation. All right. So I have 2 H pluses remaining here on the left. I'm going to add 2 OH minuses to that side. And whatever I do to the left side, I need to add to the right side as well. Okay, so what that gives then, 2 H plus and 2 OH minuses will give me 2 waters. So I have 3 Cn minus plus 2 H2O plus 2 MnO4 minus to give 3 CnO minus plus 2 MnO2 plus H2O, plus I still have those 2 hydroxides that I added. Okay, so what we will see then is that we've introduced a couple of waters here to the left side. So that will cancel out this H2O here on the right, and that'll cancel out one of the H2O on the left. So we're left with 1 H2O on the left side. So let's rewrite this. We're going to have our 3 cyanides plus that H2O that was not canceled out, plus the 2 MnO4 minus to give whatever remains, 3 CnO minus plus the 2 MnO2. The H2O cancel out over here, remember? And then we're left with that the 2 hydroxides here at the end. So the additional steps in basic solution is after you go through and you cancel out the electrons and everything else, if you are left with H plus on any side of the equation, you need to add as many hydroxides to neutralize the protons. And whatever you add to one side to neutralize the protons, you need to add to the other side. Then if any waters remain that can cancel, you cancel them out, and then you just write what remains. Okay, so yes, it is an involved process when you balance a redox reaction by the half reaction method. But again, you can double check this. You can count your atoms, you can count the charges on both sides, and you will see that it is balanced, both in terms of the mass and also in terms of the charge.